If everyone can clarify, that would be great. If you can see us, that would be lovely. On YouTube, Twitch, whatever you want. And let us know. Let us know where you're watching.
Okay, I see us on Twitch and on the YouTube.
You do, but is it on the right video on YouTube? Because mine says it's still waiting.
Yeah, it has work.
Weird. Mine says it's still waiting on mine.
Oh, really?
Maybe it's the right one.
I see it has like a loading screen. Oh, okay, never mind, not anymore.
Oh, now you're going bad.
It has sort of full loading.
What's happening here? I don't know. We'll find out.
Yeah.
Hopefully everyone can find it, because I'm not sure what's happening. Okay. And welcome, everyone. Can you hear both me and Jaden just all right? Please let us know, because no one is chatting away.
Yeah. How are you doing, Kip?
Dude, I'm doing all right. How are you doing? I just got my first dose of the vaccine today, so my arm's a little sore.
Yeah, that is good news, and we can celebrate you.
Yay!
Yay, Kip. Yay, Kip.
How are you doing?
So Kip, it's working. We have someone, Kelsey, says it's working.
That's good. I'm glad it's working, but
that's on
Twitch.
That was on Twitch.
I'm more worried about the YouTube side of things, but I think it's working on YouTube as well. So we'll just get going here.
Okay.
But anyways, for all those who are watching, welcome. It's findable, I think. I don't know what that means. It should be right, so I don't know what the issue is if it's not.
Findable. I think.
I hear you both, except I think Jaden went out. Yeah, I think.
What does that
I don't
mean?
know. I think you had maybe a slight issue for a second. I don't know.
Okay.
Yeah, who knows?
All right. Should we jump into today?
Yeah, dude. Let's jump into today. What are we going to be learning about today,
Jaden? Well, as everyone can read, energy and work, and a little bit of the dot product, but you'll figure out why that's important later on. With our work, what that just sounds like we're going to work or what?
Dude.
Kip? I don't know. What does that mean?
We're going to go work out. Get swole.
Work out?
I don't know, but I'm going to give you a hint. It's related to energy.
Well, I guess working out, I need energy to work
that's
out.
True.
So.
But yeah, we're gonna keep going along here. So let's get started, Jaden. We have, of course, like always, we have a review from last week.
Review.
Woohoo.
Awesome. And this first question is review integrals with coefficients. So last week we had a really good question on what happens when you have more than one term with a coefficient, right? And we showed an example, but we would like to do another review question on that. This week we have the integral of 4x squared plus 3x dx. Okay. First thing that I would like to do is split this into two integrals.
Okay.
Okay. Because this is a polynomial that is being, I guess, added, right? That's what it is. We can split it into two integrals. Our first one being 4x squared dx. Our second one being, so we have our plus sign, 3x dx. Okay. And now we learned our rule with our coefficients that we can just bring that on out on the outside of the integral. So this will look like a 4 integral sign x squared dx plus 3 integral x dx.
Wow, that's so cool.
Wow. Yeah. One thing that might be a little confusing is how did we get two dx's? We just multiplied it, right? Distributed in to both of these terms because it's a multiplication problem when you have parentheses. So that's how we get the two dx's, just to clarify that in case anyone was wondering. And now we know how to do these two integrals, right? We increase the exponent and divide by that new exponent, right? So we get a 4 because this is being multiplied. So 4x cubed divided by 3. Then we have a plus c. Okay, I'll just call that c1, being c1 for the first integral. Plus, we have a 3x squared divided by 2 plus c2. And we learned that when you have, right, two different, not coefficients, constants, we can add those together and just call it one coefficient or constant. Kip, I'm saying coefficient because we're working on an integral with coefficients, but I'm meaning constant.
Okay, sorry. I wasn't paying attention, dude. I'm paying attention now.
Okay. But anyways, I'm gonna finish our problem. It's gonna be over here. Woo! Our final answer is gonna be a 4/3 x cubed. That's a 4 plus. Man, my mouse is struggling today. 3/2 x squared plus c. Woo! Any questions? Any comments? Any questions from you, Kip? Anything you want to clarify or ask about?
Jaden, what does that C represent again?
That is a constant. And that means that this integral can represent a whole bunch of different integrals of the same type.
Right, I remember that.
It can be, it's in the family of integrals, right?
Well,
and
I think I'm good.
Yeah.
Yeah.
That was pretty cool.
So let's keep moving forward then. And move on to our next review question. What is momentum? So
what is momentum? Yeah. What is it?
I don't know, Jaden. It's mass times velocity.
And doesn't it like P equals? And did you ever figure out why it's a P?
No. Because they ran out of letters.
It's probably like something different language or something. But yeah, so you were saying it's P equals mass times.
Yeah, that's what I'm saying. And remember, momentum must be conserved, meaning that unless something is acted on it, that it will keep the same momentum. And also,
Okay.
and that's going to be kind of important going into tonight. And then also along with that, we're going to be, or along with that, right? If you apply a force to a momentum, then its momentum will change. So
You apply a force. Okay. Cool.
cool. So I think that's enough reviewing momentum. Should we keep moving forward? Whoa, Jaden, we're on to
Yeah.
something called the dot product now, and that's looking a little spooky.
Okay. Yeah. Super spooky. Uh, so what we need to know about the dot product is it's a
So we
way
have a comment
to
saying P
multiply
because Peleus is
vectors.
Greek for momentum. Huh. I don't know if that's true,
Oh,
but
cool.
I'll take your word for it. Maybe you Googled it.
Yeah, cool. Okay, so what we need to know about the dot product is it is a way to multiply vectors.
Okay.
Okay, and we multiply the vectors to get a scalar.
Okay.
Okay, so you change vectors into a scalar. And what a scalar is, it is just the number, right?
Exactly. It's the
Vectors,
it's the
you
Department of Transportation product.
have.
I didn't think that was true, but thank you for making us believe that it was for a second.
Yeah. So what was I saying? Oh yeah, the scalar. What is a scalar? It is just the number, right? A vector is magnitude, direction, right? You have the direction involved with it. The scalar is just like the magnitude or the direction, right? Just one or the other, just the
Right.
number. Okay, it doesn't have both. Uh, and why is that important? Uh, because you'll see later in our lesson.
Wow, Jaden.
You're gonna.
Should we do an example?
It's
Should we
a
help them out through one?
yeah. First I'm gonna talk about these
Oh, yeah, go
subscripts
for it.
and let
That's
stand.
a good idea.
So when we have a equals a1, a2, dot dot dot, an, that's just meaning this vector can be as long as many terms and I guess dimensions as we want. Okay, up to n. Uh, and same with the b. And the dot product is represented by the dot. It looks like a multiplication symbol, and sometimes it gets confused with the multiplication symbol. Uh, so you just kind of have to know that if there are vectors and there's a dot, it's the dot product. If it's just numbers and a dot, it's a multiplication. That's how you can tell the difference. But anyways, it is the sum from I equals 1. So that means just your starting one, like an x, y, z. If you had three terms, it would be your first one. So the x all the way to n, which would be your z term. And that looks like this. So a1 times b1 plus a2 times b2, yada, 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 on to the last term.
Yeah.
Okay, now let's do an example because that might not have made tons of
Okay,
sense.
let's move on to an example.
All right.
Do.
So our dot product example, we have two vectors. Our first vector is 1, 3, 5. Our second vector is -2, 2, and 1. So we're working in 3 dimensions, right? That's kind of our normal thing in this world, right? 3 dimensions. So the dot product says we take the first two terms from each vector, we multiply them together. So we have a 1 times -2. I used the X here because I didn't want you to get confused with the dot product.
Okay.
Uh, Gotta add each term together. Next term would be a 3 times 2. Our last term is 1. Let me know in the comments if you understand where I'm getting all of the numbers. And then we can clarify a little bit more.
Yeah.
But anyways, that all equals 2. The negative 2 comes from the 1 times negative 2. Plus 6, that came from the 3 times 2. Plus 5, that came from the 5 times 1. And that, when added together, equals 9.
Dude, that's so mathemagical. If my
Yes.
mathemagical button... wait, it's not that anymore. It's that now. Wow, there we go. Boink. I forgot.
Oh,
I
Kip,
switched...
you're muted.
I'm muted?
I think.
Oh. That's weird. I muted you on Skype. Sorry. I wasn't muted. I don't...
I just
Jaden,
turned
come
off
back.
the
There
video
you
for
go.
a second.
Yeah, sorry. Okay. You left me. Yeah. Anyways. Thanks, Jaden. Yeah, so just real quickly, right, you do the 1 times that, boink, that times that, and that times that. You just kind of line them up and go. Anyways. So that...
And that can be as like terms as you want,
Right.
right? It can be up to n, and n represents any integer.
Right. But for tonight, we're just going to stay with 3, right? Because in our world, we have 3 dimensions. And so our vectors, for the most part, are only going to have 3 quantities max. Sometimes they'll have even less.
Yeah.
So, yeah, we'll just keep chugging along here. And we're going to go ahead. So now that we know what the dot product is, should we move on to talking about something else called work?
Yes, please.
Jen, do you work, dude?
Yes. Dude, I work. I've been helping some kids these COVID times with their schooling and
Nice.
stuff. Do you
Dude,
work,
I
Kip?
kind of work sometimes.
Kind of been doing
Yeah.
the same, helping people with COVID
Wow,
times.
Kelsey's world has 5 dimensions. That's pretty cool. So, anyways, let's get back on track here to work equals force times ds. So what on earth does this mean? So we've got an integral. So we know we're going to be...
Is that a times or is that a dot product?
That's
Kip?
a dot product, Jaden. So the first thing we know is that because we know it's a dot product, what does that mean, Jaden? That means that work is going to be a what kind of quantity? A scalar quantity.
Scalar.
Scalar. So
That's so
it's
cool.
not a vector. It only has a magnitude, right? It doesn't have a direction associated with it.
Right. Huh. That's cool. So
that's the first thing we can tell. But then we can go into it a little more. So what on earth does this deal mean, right? So we have the integral. So we know we're going to be doing a whole bunch of additions, right, of some sort. Right. And then we've got...
Right.
It's times the dot product of the force times something called ds. And what that ds is going to actually end up being is it's going to be a vector quantity for a small movement in the x, y, and z direction all at once. So if we hop on over to the Jamboard, I'll kind of show you what I mean by drawing it out a little bit here.
Okay.
So we've got, let's say that we've got an object, okay? And if we remember back, we can just draw an object as a box, okay? And we're going to say that there's a force on this box pushing it this way with a force F. Okay.
Uh,
And in
okay.
this case, we're working in really just a one dimension, right? It's only moving in, we're going to call it the x direction. So essentially,
Okay.
we have this little kind of tiny chunk that equals dx, right? So in this case, ds just simply equals dx, right? But
Right.
normally it would equal, it equals technically ds equals, dx, comma dy, comma dz. But
Right.
in this case, our dy and our dz are both 0, and we're going to just leave it in a one dimension because we haven't taught you guys how to do 2 or 3-dimensional integrals yet. Anyways, so
Yeah.
every time we move this box a little distance, a little bit of work is done, right? And so if we
Right.
want to figure out how much, um, if this is our distance x, if we want to figure out how much work was done on this box in that distance x, well, we'd take the integral of f ds, and in this case, it would be f dot dx, right, Jaden? And
Right.
so in this case, we'd get the integral of f. We'd have fx, right? Because we're taking the dot product. So we'd have fx dx. And lo and behold, when we take an
Right.
integral of this, because force is constant, right? So we can pull our force out front. So we have f integral dx. And anytime you have the integral of just something like dx or d anything, it's just going to equal that very, yeah.
X.
And so we're going to get
That's so cool.
work. Let's see here. If my pen will write, my pen's freaking out all of a sudden. Work equals fx. So what does that mean? Well, that means that work is simply going
Whoa.
to be the work
Uh-huh.
is going to simply be the force times the distance it travels in that direction, right?
That's so
That's so
cool.
cool. But there's a part about this, Jaden. Let's say that this box is moving in the x direction still. Okay?
Yeah.
But let's say we have a force that is going up, and we don't have the force that's moving in the x direction anymore. Okay? But the box is still moving in the x direction. Is any work being done on this box? So if it's not moving up, it's moving in the x direction, not the y direction. Only in the x direction, but there's a force being applied in the x direction. Is work being done on this box?
I you cut out a
Oh,
little bit, so I didn't hear the full
so
question.
that's
Sorry.
okay. So if we have this box, right, Jane, and it's moving with a
Yeah.
constant velocity in the x direction. So let's say it's a box on ice, okay?
Cool.
And
Okay.
then
Just in
yeah,
space.
it's in ice skates, okay? And then to help reduce friction even more, let's say we have a force pulling up on it to make it less weighted, right? Um,
Okay.
but it's not moving in the y direction, it's only moving in the x direction. Is there any work being
Uh-huh.
done by this force in the y direction?
Any work being
Is
done on it?
the force in the y direction
In the
doing any
Y?
work?
No.
And why not, Jaden?
Because it didn't go anywhere in the Y direction.
Exactly.
Right? Our work needs that displacement to be work.
Right. But even though, right, we have this f, but this isn't true in this case, right? Because this is technically an fy, and because it's fy, right? This, well, let me
Uh-huh.
say it this way. So we have work done in the x direction if there's a force in the x direction, right? But there's not a force, or there's a force in the y direction. So if we want to take the integral again and see if there's just a force in the y direction, right? So we have f of y. It's still moving in the x direction. We have this dotted into dx. Well, when we take the the dot product, right, of our force into our movement vector, right? You would have 0 comma f of y comma 0, and then you would have that dotted into
comma 0 comma
so you'd have
0.
x comma 0 or dx comma 0 comma 0. So everything in this case would equal 0. And that's why you have to have this dot product, right? So, and we'll get into a little more of why that is in the next slide, and this idea of what energy is and how work and energy kind of relate to each other. But the idea being that if you have a force moving in a direction that is not in the direction of the object's movement, then that force is doing 0 work, right? Also, if the object is not moving, 0 work is being done. So a good classic example of this, Jaden, would be, let's say you stuck out your arms and held books in your arms, right? Your arms would get really, really tired eventually if you just had your arms straight out and held the books in them.
Just like,
yeah. But the thing is by physics definition, those books didn't move anywhere. And so you would have not done any work. Even though your body's getting a workout, you actually haven't done anything physically to create work. So that kind of leads to what actually is work. So its units are in joules, and what it actually is it's the addition or subtraction kind of energy from a system. Okay? So let's move in then to what energy actually is.
Yes.
So, like I kind of said, it's the amount of work put into a system. Okay? So, let's say that I have a block of, I don't know, or let's say I've got Jaden, okay? And I start pushing Jaden, right? Jaden's now moving. So I did work on Jaden because now Jaden has energy inside of him. Okay? He's...
Dude.
Because...
Thanks for energizing
Dude, you're so welcome.
You're the Energizer Bunny, dude.
Yeah, dude, I sure am. So, like, how this works out, right, is energy can be stored kind of in two different main forms as far as mechanics are concerned, right? There's other types of energy out there to some extent, but there's this idea of potential energy and kinetic energy, okay? So the kinetic energy, or I guess starting with potential energy is stored energy, all right? So if you do work on something and it stores up energy, then now that object has potential energy, right? It's ready to explode, right? It wants to go somewhere because now it has energy. And then...
So examples of this would be like the rocket at Lagoon, right? You lift up the rocket, it's all the way at the top. That's storing the potential energy. When it releases it, zoom, it falls down really fast.
And that zoom,
or anything.
So anything, right? Like a roller coaster is a great example too. So the work being done is when you're getting lifted up, right? Like, so at the rocket at Lagoon or a roller coaster, as you're getting lifted up, there's a force acting on you for a certain distance, and you're building up energy, right? There's work being done. It's building up energy. And then you're at the top, and now you have a potential energy. So then when you let go, right, then that person now is falling, or if you're on a roller coaster, you go down the hill. Whoa! And from there, that's switching now. So you're going from potential energy to kinetic energy. So kinetic energy is energy that is moving, right? And so the thing is, though, is that this energy that you have cannot be created or destroyed.
So, Kip, where does it go?
What do you mean, Jaden?
Like, if I am up on the roller coaster,
Yeah.
and then it turns into kinetic energy, but when I'm at the bottom, where did all the energy go? If it can't be created or destroyed.
We'll get into that in a little bit, but there's a very important part about this, right, Jaden? Which is this idea that, like you said, it turns into kinetic energy, right? So that's the first thing, is that if you have a lot of potential energy, at some point it's going to get turned into kinetic energy. And so, like at the rocket, when you drop, right, you turn into kinetic energy, okay? And on a roller coaster, it's the same thing. And on roller coasters, actually back, before they had a ton of technology to help slow down rides and all these kind of things, they would actually design roller coasters based off, and they still do a lot of it, based off this idea of conservation of energy. So they know if they lift you to a certain height, right, and then let you go, they know how fast you're actually going to get going by the bottom, and so they know how to like make sure that you don't go flying off the track, essentially, based on this idea of conservation of energy, which is really, really cool, because like you look at old roller coasters and they really are quite an amazing mathematical feat, because they calculated every single one of those hills and how high they needed to be, because if the hill was too low, right, you'd have too much kinetic energy still, and so you could go launching off the track. And then if you didn't have a high enough hill, or if you had too high of a hill, then you would drop back down. And so you actually have to get like right in the sweet spot to make sure that you almost run out of kinetic energy and turn it back into potential energy up at the top. So but let's go into this and kind of derive how you solve for both potential energy and kinetic energy in a system. So we've already just kind of stuck out the answers here, but we're going to kind of derive them here in a second. So potential energy is just going to be mass mass of the object times the acceleration of gravity times a height. Okay, so this is gravitational potential energy. There are other types of potential energy as well out there. There's spring potentials, others, but for our case, we're just gonna stick with gravitational potential energy, right?
Sounds good.
Why is this important, Jaden? Well, the first thing that we'll notice from this equation, if we remember back when we talked about weight, right? Weight is a force, which is equal to the mass times the acceleration of gravity. So we can see that right here, right? This mg.
Yeah.
So that's our force. And if we remember back to the definition of work, it's just going to be the force, right, times a certain distance. Well, that's where this h comes in, which is the height.
Whoa.
And so
the potential energy is essentially the work that you put into something to raise it higher.
You're exactly right, dude.
That is so cool.
Because remember, work gets stored, right, as this energy.
Right.
And so that's kind of, that's where it's really cool, right? So you do this work, and now that has potential energy. Okay? So what about kinetic energy? Because that doesn't look anything like anything we've seen before, right? There's no force hidden in there. It looks kind of wacky and weird.
Yeah, that does look very weird, Kip.
So let's see if we can get to that answer, shall we, Jaden?
Yes.
So I'm going to switch over to our Jamboard here, and we're going to start deriving this.
Okay.
Well, I guess we could technically, if we wanted to really quickly derive, we'll just derive really quickly the potential. So remember, it's the integral of f dot ds. And in this case, our ds is just going to simply be dy, right? Because we have this box and we have a force of gravity pulling it down. And this is going to be f. And f equals mg. So we have the integral of mg dotted into dy. And this mg is just going to be constant. So you get mg integral of dy, which equals mg y, and in our case we're just going to say that y is the height, right? Because and so we solved it. Look at how easy that was. So that
wasn't
solved.
Nice.
So now let's keep moving on, and now we're going to get to do some really lovely math. So how do we find kinetic energy? Well, if we remember back from last lecture with momentum, we can actually say that F is equal to dp dv, right? I think that's right. Or is it dt? It's dt, right?
Yeah, dt.
Whoops.
That's okay.
So then we have this dt, and then
that's the change in momentum over the change in time.
Okay. Oh, sorry, I don't need to write that yet. Okay. So how does that matter? Well, then we can write the integral of dp over dt, and this is dotted into ds, right? And so trying to remember how to go from, okay. And then I think because we multiply these together, you get the integral of dp ds over dt. Okay.
Okay.
And well, this whole thing is over that, right? And then Jaden, what is a ds over dt equal to?
Is that velocity?
The velocity, right?
Holy taquitos.
So we get the integral of dp.
Oh, so cool.
I guess that, and we get the integral of dpv. Okay. Now, where do we go from here? Well, dp is the change in momentum, right? Well, what do we know about the change in momentum? The change in momentum, if our mass is constant, is going to be m times
v.
But it's going to be the change, so it's going to be dv over dt.
Yeah.
Okay.
Nice.
So let's keep moving. So now,
should we go?
Yeah.
Or are you still working?
No, I moved to the next page. So now we've got dv over dt v, and we have this m out front here. Okay. And I feel like I am missing something somewhere. We're almost there.
You still need that. What did you need?
It's that dt is the only thing that's confusing me. Somehow that dt I think is supposed to cancel out. Because we need it as mdv.
So
mvdv. So that dt needed to vanish somewhere.
The ds, that would be, let's see, so in our, over here, our ds should be a v dt, I think.
Wait, what?
Our ds?
Yeah. Oh.
Should be dt instead of
V.
Yeah, instead of just
right.
v.
Okay. So yeah, we'll say that ds. Did you ever play the ds? So we have ds equals
Yes.
v dt. Is that what you're saying?
Yeah.
Okay.
And then
from there,
so we have the dt over dt time, or dot v dt.
right. So we'll leave this as dot v dt, and then when we move over to the other slide here, then we get m. Let's see here. We get m dv dt, right? And then we have that times dv dt, or no, wait, that's all over dt, right? dv over dt. Is that right? Like this?
Well, the let me see real quick. Where were we?
Dude, we... No, that wouldn't...
So we should have... we're missing the V, I think. Just the V without DV.
Oh, okay. Yeah. This is... Wait, so like... It's V?
Because our DT should cancel each other, right?
You're right. But does that... That doesn't... Okay. Wait, we have another DT, though. No, wait. Now I'm confused. Okay. Yeah. Okay, yeah, we're right. So we've got this. We've got mdv times v dt all over dt. Sorry, that was a bit confusing there. And so then you can cancel out your dt's, right? And then you're left with the integral of m v dv, which equals 1/2 mv squared. And that is so solved now. Ching! And it's pretty mathematical. Whoa, what'd I do?
It's definitely a lot more difficult to just see, right?
Yeah, it's not easy to see, but
you muted yourself. again
Sorry,
for
dude.
me.
Oh, I know why. I know why that's happening. But sorry.
It's all good.
Um, anyways, but yeah, so we've got this. It's definitely not easy to see. Um, it's just really cool math. At least it's like nerdy math
No, that's really
for
cool.
me and Jaden, I think. Um, but the important takeaway for all you guys watching is the fact that uh, there's kinetic energy, potential energy, mass is important to both of them, right? And then the velocity is important to kinetic energy, and the height is important to gravitational potential energy.
Right.
So let's keep moving on then and talk a little bit more about something, and then maybe we'll even play a fun little video for you guys.
What?
Okay, so Jaden, you asked something really good earlier. You asked what happens to the energy then if it's not, if it's supposed to be conserved, right? So in the case of, if we go back to the
Right.
rocket, right, there's potential energy that's
Uh,
added by work when it goes up, and according to the conservation of energy,
yeah.
this energy should never go away. So when you drop,
Right.
you should die, right? Because you have all this kinetic energy, and then bam, you're going to hit the ground. And like we talked about last week with momentums, you're going to have an instantaneous stop, and your momentum's going to go to zero real quick, right?
Oh yeah,
Yeah.
that wouldn't be cool.
No, that wouldn't be cool. Um, but what you can actually, there's actually something called conservative and non conservative forces. So, what does that mean?
Okay.
Because energy is always going to be conserved, right? But like I said, there's different types of energies out there. So a conservative force is
Right.
something like gravity, right? So you bring something up, you let it go, it's always going to have that same amount of energy. That's why orbits work. That's why
Right.
all these kind of different things work, is because there's conservation of energy and it's a conservative force, meaning that it
Okay.
keeps its its mechanical energy the same. But there's
Right.
another kind of forces out there that are called non-conservative forces. And one of the biggest classic examples of a non-conservative force is something called friction.
Oh, friction.
Yeah. So let's go back to something we did a little while ago, Jane. Let's rub our hands together. So as we're rubbing our hands together,
Wow, Kip, my hands are getting
but
hot.
why, Jaden? What is happening in between your two hands? What kind of force is happening there?
Friction.
Friction! And that friction causes what kind of energy if your hands are getting hot?
Uh,
It's not going to be.
non-conservative guessing, and then it's going to be a kinetic energy. Uh, and the non-conservative means that some of my energy is turning into heat.
Heat. Nice, Jaden. High five.
Yes.
So, exactly. So, as you rub your hands together, they get hot, right? So, that energy is leaving the system, but it's leaving the system as heat energy. It's transferring to another type of energy.
So if we all of the heat, then our energy would never change. In like the roller coaster examples.
Exactly.
Just, uh,
Yep. And friction actually does work, right? And so it takes energy out of a system. Remember, I said work can bring energy into a system or take it out of a system.
oh,
And so when you're trying to, calculate the total energy of a system, and there's a friction force, you actually have to subtract that friction work out. So you have to take it
Yeah.
out of the
Okay.
system, right? And then if you added it all back together, it would still be the same amount of energy. So why on
Okay.
earth is all of this so important? Well, because Jaden, we live in a world that is energy hungry, right? Everything we use and do uses some sort of form of energy. There's work associated with it. And the thing
Yeah.
is that all this energy has to be conserved. There's no way to create more of it. Um, and so lots of people will come up with these ideas, such as a perpetual motion machine, right? They come up with these ideas of ways that they think they can actually make energy. Um, and so, why this is kind of a, you know, it's an interesting thought experiment is people will say things like, well, if I'm driving down the freeway, why don't I just put a giant wind turbine on top of my car? And that way I will make energy. But the problem with that is, right, the only work that's being done is being done by your car's motor. And so as you
Right.
drive, the wind from, the air resistance will spin that motor. But the thing is or spin that wind turbine. But the thing is air resistance is actually a non-conservative force. It creates friction, it creates drag. And so if you put this giant windmill on top of
Right.
your car, it's actually going to be less efficient than if you didn't have one on there because you can't create energy from nothing. So
Right.
that's something really, really important in the rules of physics. Um, and then the other thing that maybe we'll touch on next week to show kind of how cool this is when you remember a few weeks ago we were doing projectile motion, Jaden, and we were trying to calculate these heights and all
Yeah.
these kind of things. And it was kind of complicated. We
Yeah.
had to take these integrals, or we had to, find or take derivatives to find the maximum. Well, the thing is, because
Uh.
of conservation of energy, we can actually find that max
Uh.
height very, very quickly. And so we can actually, because the
Whoa.
energy has to be conserved, right? So it can't.
Okay.
And so you can switch that kinetic energy to potential energy and find that height really quickly. It's kind of a cool thing. And we'll maybe need to
Okay.
do that for a review next week. But to end for tonight, because we're almost out of time, I want to show you guys a little video that I took earlier today, and we'll see what you guys think.
Please. Ah, Kip. Damn. In our plate. Okay. Uh, because of our non-conservative forces, there's air around you, I'm guessing, in that video. And the ring, you're in a vacuum, dude? Are you human? Wait, Kip, we got a comment saying that you're muted. Yeah, that's weird.
All together. So we'll just turn that on and hope it doesn't sound horrible. Does it? Oh, I know why. Okay. Yeah, I know why that happened. Whoops. I don't know if that sounds okay. It might sound really bad. Um, Anyways, so we'll keep going here. But let's watch it one more time. But yeah, Jane, the idea being that there's non-conservative forces, right? So there's friction in the chain, and there's air resistance, like you said. And so it's not going to come up and hit me in the face. It doesn't get as close, right? But let's say we were in a perfect world where there was no friction and there was no air. Would it smack me in the face hard?
Dude, I hope so. That'd be funny.
But it wouldn't, would it?
Well,
The reason being,
the
right, there's that conservation of energy associated with this, right?
So
when I let go, and it comes, now I'm gonna have. So when I let go, it comes and hits, or when I let go, there's a potential energy, right? As I let go, it transfers to kinetic energy, because gravity is now doing work on it. It swings through, and it goes up the other side. Now that kinetic energy is slowly being transformed back into potential energy until it reaches the top.
Right.
And then it comes back. Gravity does work again, turns it into kinetic energy again until it comes right back close to my face.
Yeah.
And then at that point, it turns back into potential energy. And so right at my head, it's all potential energy again. And so this is actually an experiment, guys, that you can do yourselves at home. Find some sort of rope or something, tie something to it, hold it up to your head, let it go, and see what happens. Just make sure the rope is tight.
Just
don't step forward.
Don't
step forward. But that's, one of the most classic examples of conservation of energy. I'll show it one more time here. Ready? Here we go.
Yes.
So anyways, Jaden, the idea being that it's really quite magical. And thank you guys for tuning in. We'll see you on Thursday for all your homework questions that you have.
Yes.
And if you don't have homework questions, you can join just anyways. Or watch us next Tuesday when we probably start to spin things up a little bit and get into rotation.
Heck yeah.
Gonna get a little twisted.
Try not to flinch too.
Yeah.
True.
But thank you all for watching.
Well,